Hello everyone, welcome back to our session with respect to the acids and bases in the context of our chemical process. So let's quickly review what we have been discussing in the last session or last lecture session anyway, and then move on to the relevant applications, I guess, right? So I believe we looked at primarily deriving the Henderson and Hasselbalch equation, and that gives us an idea of the relationship between pH, pKa and the relative concentrations of the deprotonated and the protonated forms, right. So looking at those or looking at that equation, we can get the relevant graphs, pH and concentration here, and as we see that as the protonated form decreases in concentration, the deprotonated form is going to increase in concentration. Pardon me, this is the negative symbol here, and thus where the concentrations are, both of them are equal, that is going to be the pKa value, right. And what is pKa? pKa is the negative logarithm of the acid dissociation constant, right, and this is what we discussed. And I believe we also discussed examples with respect to application of nitrogen, yes, and we saw that the farmer would be better off if he applies nitrogen in the form of ammonia. Why is that? Because at neutral pH, right, NH4 plus will stay as NH4 plus and not as NH3, but while HNO3 and NO3 minus, HNO3 would stay as NO3 minus at pH 7 and NH4 plus would stay as NH4 plus at pH 7. So this is a cation, this is an anion, and because the soil has a cation exchange capacity or it can absorb cations, the farmer is better off applying nitrogen in the form of ammonia now, right, or ammonium. So and then we also looked at the example of removal of arsenic. So there are two forms, H3AsO4, that is here, and H3AsO3, and this is the more oxidized form obviously, right, and we saw that this particular form is neutral or has no charge at the neutral pH or around pH 7, but thus more or less I believe is in the deprotonated forms, right, and so this has or this is in the form of an anion, and this can be removed by the ion exchange process, right. This is what we were discussing earlier. So let us move on to the other sets of examples that we have here. So I believe we are also going to look at silicic acid. So if somebody wants to remove silica, let us say, from your water, let us say, if it is an issue, and you know that the pKa1, I am talking about H4 SiO4 here, and if I want to remove silica by ion exchange, let us say, or electrodialysis, and the pKa1 is 9.84, pKa2 is 13.2, right. So let us look at that again, and what does this mean? This is H4 SiO4 and the next deprotonated form, and again the next deprotonated form. Let us label them H4 SiO4, H3 SiO4 minus, H2 SiO4 2 minus, and the pK values are 9.8 and 13.2. So at pH 7 everything is going to stay as H4 SiO4, which does not have a charge, and thus obviously it can't be removed by ion exchange process at the neutral pH, right. So let us see the other example. So CH3COOH, we are going to look at that in greater detail later on, but in general the issue is that acetic acid will be produced in anaerobic digesters now, right. And the issue is that as you see the pKa is not relatively low, it is around 4.76, right. So that means acetic acid is not a strong acid, yes, but the key here is that when acetic acid is produced in your anaerobic digester, the pH can fall to let us say 5.5 or around 6 depending on the quantum of the acetic acid produced, right, and thus is good enough to ruin your anaerobic digestion process. So that is the reason why we need to look at acetic acid in greater detail, even though it is not a strong acid. As you see, its pK is 4.76, right. So anyway, we will come back to this again. Let us look at the other example. And I guess one example that we have here is with respect to two toxic gases, hydrogen sulfide and hydrogen cyanide. And in general, with respect to gases, we want to see at which particular pH would they be volatile, and at which particular pH will they not be, I guess, volatile, right. So as you see here, with respect to H2S, let us say, this is H2S, HS minus, S2 minus. So this is around 7 or 6.99, and this is 9.25. And what do we see here? So at pH 7, right, there is considerable amount of H2S present, or the neutral molecule, let us say, or the protonated form which is neutral, and so it can be volatile or be stripped out of your solution. Now what does this mean now? So let us say if this is the aqueous phase and this is the gaseous phase, if it is in the form of HS minus or S2 minus, being negatively charged and water being a polar compound, it will be relatively difficult for these two compounds to escape into the gaseous phase, not escape, pardon me, change phase into the gaseous phase. But if it is in the form of H2S, which it can be at around pH 7 as you see here, right. So it can change phase into the gaseous phase. So same case with hydrogen cyanide, right. And so what do we have here? Again, these are not to scale, so please keep that in mind. So the pKa is 9.25, this is for hydrogen cyanide, right, and pH 7, let us say somewhere here. So you see almost all of it will be the protonated form with no charge. So thus can change phase from the aqueous phase to the gaseous phase because there is no charge on it, right. Anyway, charged compounds like HS minus, S2 minus and Cn minus, and water being polar, they would want to stay in the aqueous phase. Anyway, so here we see some applications of where pH would affect your natural or even engineered systems. So we are going to look at what do we say, the monoprotic, diprotic acids and triprotic acids and what they are about in greater detail now. So let us move on, why waste time please. So here we are going to come up with a new term called the ionization fractions. So let us look at, or let us define what they are. So in that context we need to look at monoprotic acid. An example is HCl, I guess, right. It has only a single proton to donate, so that is a monoprotic acid. So the usual example we are looking at is HA dissociating into H plus and A minus, right. So and let us say if I define total acid as being equal to HA plus A minus, right, I will now define ionization fractions such that you will have two ionization fractions for a monoprotic acid, alpha naught, that is going to be equal to the protonated form, concentration of the protonated form by the total acid, and the second ionization fraction alpha 1 is going to be the concentration of the deprotonated form by the total acid concentration, right. And this is how we define the ionization fractions. And why do we use them, I guess? So let us say if you know the pH of a particular solution, let us say, right, and you want to calculate what is the fraction of the deprotonated form and protonated form for your own or various purposes, let us see. So rather than going through the calculations, just looking at the ionization fractions for that particular chemical or that particular acid or base would give you an idea about what is the fraction of your acid or total acid, pardon me, that is going to be in the protonated form or is going to be in the deprotonated form, right. So let us look at how to calculate these aspects, I guess, right. So what do we have here? We have alpha naught is equal to concentration of HA by A total, and that is equal to concentration of HA. So again, if it is not yet clear, what does alpha naught give you an idea about? The fraction that is present as the protonated form, right. That is what you see here in the numerator, protonated form, right. And what does this give you an idea about? A fraction that has deprotonated, let us say, right. So, that is what you get an idea about. So, anyway, moving on. So, we have alpha naught equal to HA by A total, and A total we know is the total acid, it is HA plus A minus. So, dividing by HA, let us say 1 by 1 plus A minus by HA, right. So, I guess we want to represent it in terms of what now, pH, because we usually look at what is the, how is the ionization fraction changing as a function of pH, yes, and some other constant, and the constant usually that we use in your acid and base is obviously the acid dissociation constant. So, let us look at the acid dissociation constant for a second here. So, Ka for this reaction, and let me rewrite the reaction here, HA goes to H plus A minus, or dissociates to, I guess, right, and the Ka is activity or concentration. Let me go with concentration here. In general, as you know, it is going to be activity, but I am approximating activity by concentration here by HA, and the fraction that I am looking for is A minus by HA. So, that particular fraction deprotonated form by HA is going to be equal to Ka by H plus, right, and this is what I have. And so, I am looking at this particular equation here, right, and I am going to substitute this variable A minus by HA with Ka by H plus. So, more or less alpha naught, which was earlier 1 plus A minus by HA, concentrations of A minus and HA obviously is going to be equal to 1 by 1 plus Ka by H plus, and that is going to be equal to concentration of H plus by Ka plus H plus. So, as you now see, alpha naught is a function of pH or H plus and a constant Ka. So, for a given compound or monoprotic acid, you can calculate alpha naught. So, similarly, alpha 1, what is that going to be? It is nothing but if you look at the definition the way we defined it, it is going to be 1 minus alpha naught, right, and that is going to end up being Ka by Ka plus H plus. I mean, you can do the derivation again, but obviously you know that alpha naught plus alpha 1, the fraction should equal to, the sum of the fractions should equal 1. So, we can always calculate alpha 1 by 1 minus alpha naught, that is equal to Ka by Ka plus H plus. So, keep in mind that there are two aspects here. So, it is like as if the denominator is going to be the same, right, that is obvious, and the numerator 2 is H plus here in this case and Ka in this case, right. So, I believe let us look at one example here, and here I have a figure, and I believe this is for acetic acid. So, I think the pKa is around 4.76. So, here on the x axis you have the ionization fractions, relevant ionization fractions. So, HA will be given by alpha naught and A minus by alpha 1. So, looks like this figure is to scale. So, let us use this to understand what it is that we have talked about in the past, right. So, ionization fractions on the y axis and pH on the x axis. So, as you see at pH 4.7, which is the pKa value, right, what do we see there? We see that the concentrations of both the fractions, right. So, here the example is for acetic acid dissociating into H plus and the acetate ion, though they are representing it by HA, right. Anyhow, so we know that the pKa value for acetic acid is 4.7 or 4.76, I guess, right, and at that pKa value, you know that the activity or the concentration of your protonated form should be equal to the activity of your deprotonated form. So, that is what you get from your Henderson-Hasselbalch equation, or even when you look at the figure, right. And when I look at this figure, what do I see at the pKa value? Obviously, the ionization fraction is going to be 0.5, right, because when we say HA equal to A minus, so that is only feasible when alpha naught is equal to alpha 1 is equal to 0.5, right. So, that is what you understand here. So, because this is to scale, let us see, let us try to look at some of the concepts we looked at earlier too. So, at pH 7, let us say if I am going to look at it pH 7, and if there is any acetic acid added at either pH 9, 8 or 7, as you see it is going to dissociate to H plus and Ac minus, and the deprotonated form Ac minus is going to predominate, and you have little to none of your actual acetic acid HAC or the protonated form. But as you move towards the pKa value, let us say we will now look at pH 6, and what do you see? I guess now the fraction changes such that I guess it is going to be 90%, let us say around 90. I guess we can calculate that from the Henderson-Hasselbalch equation again, right. Still Ac minus is going to predominate, and now though you are going to have some form of the acetic acid in equilibrium with your acetate ion, and as you move further towards your pKa or at pH 5, you will see is that the fraction changes in favor of HAC here, yes, and now the trend is going to reverse as you decrease the pH beyond the pKa, and obviously at pH 3, what do you see here, that almost all of your acid is present in the deprotonated, the protonated form, and little to none of it is present as the deprotonated form. So, what does that mean? If I add acetic acid to a solution at pH 7, assume that there is a beaker here and the pH is 7, not 7, pardon me, 3 here. The current what do we say concentration of your H plus, if I look at, and the pH is 3 of your solution now, and I add some acetic acid, relatively low volume, but let us say at higher concentrations, let us see. It might change the pH by little to none. Why is that? Because at pH 3 you see that almost all of it will stay as acetate or acetic acid, and thus it will not release the proton, right. Very little or if minute fraction of it will stay as Ac minus or will be in the form of Ac minus, and thus very little H plus will be released. So, there will be little to no change in pH at pH 3, right. So, that is what we see here. So, let us move on, and I guess now we are going to move on to diprotic acids. So, in the same case we can come across develop ionization fractions. So, for diprotic acids now we are going to have 3 ionization fractions. So, let us see what they are, I guess, right. So, the first one will be a diprotic acid, I am going to say it is going to be H2A, the protonated form by the total acid, and what is the total acid in this case? Obviously it is going to be equal to the sum of H2A plus concentration of HA minus plus concentration of A2 minus, and in this case HA minus by A total, and again we can have HA, pardon me, it is going to be A2 minus by A total, right, and this is what we have. So, for a diprotic acid we are obviously going to have 3 fractions H2A, HA minus and A2 minus, and thus we are going to have 3 ionization fractions, right, and we can go through the derivation, but more or less it is relatively intuitive. Let us see if I can get that right here. So, alpha naught is going to be equal to, first I am going to write the denominator here. So, it is going to be equal to H plus square plus concentration of H plus into the first acid dissociation constant plus the product of Ka1 and Ka2, right. Ka1 and Ka2 are the 2 acid dissociation constants for your diprotic acid, and the numerator is then going to be H plus square, and similarly though alpha 1 is going to be H plus into Ka1 by the same denominator, which is H plus square plus H plus into Ka1 plus Ka1 Ka2. Please notice the similarity with respect to the equations or the fractions we derived for the monoprotic acid with respect to the denominator, and how you can approximate your particular numerator too, right. Anyway, we can derive these, but these are straightforward equations here. So, Ka1 by Ka2 by H plus square plus H plus into Ka1 plus Ka1 Ka2, right. So, these are the 3 ionization fractions that we have, and examples of diprotic acid, H2CO3, carbonic acid, which is widely present in nature, and we will see why later on anyway. So, I believe here I have the ionization fraction for that, and I believe the pKa values are going to be 6.3 and 10.3, right. So, here you see the ionization fractions on the y axis and pH on the x axis. So, as H2CO3 initially, right, at here they are starting the graph from pH 4. So, makes sense, because even below pH 4 it is going to stay only as H2CO3 or in equilibrium with carbon dioxide, obviously, if there is a gaseous phase. So, initially it is present only as H2CO3. As I keep approaching the pKa, H2CO3 starts dissociating and forming HCO3 minus, that is what you see here. Let us say if I am at pH 5, what do I see there? So, most of it is still as H2CO3, but now I see that there is some release of H plus and thus formation of HCO3 minus, right, and this is the graph for HCO3 minus, obviously, right. And as I keep moving towards the pKa, I see that the ionization fraction decreases, or the concentration of H2CO3 decreases, while the concentration of HCO3 minus increases. And once I am past pKa or at pH 7, so once I am at pH 7, what do I see here? I see that most of it is now in the form of HCO3 minus, and fraction of it may be 0.15 or so, I guess. HCO3 is in the form of H2CO3, right. And so, as I move further at around pH, what is it now, 8.3 maybe, yeah, 8.3, looks like everything is going to be in the form of HCO3 minus at around pH 8.3. And then as I move further away from or increase the pH and move towards pKa2, I am now going to have, so initially H2CO3 was dissociating into HCO3 minus and H plus, right, that is what we see here. I mean, pardon me, here, let me highlight that again, please. So, initially H2CO3 was dissociating into HCO3 minus and H plus, and that is what you see here as H2CO3 decreases, right. At the same time HCO3 minus is increasing, and here at a particular point you have no H2CO3 at all, I guess at 8.3, and here at 8.3 everything is in the form of HCO3 minus, right. And then as I keep, and what is the Ka or pKa for this particular equation? It is 6.3, and that is what we see here, 6.3. And then you have the other acid dissociation, HCO3 minus dissociation, that is going to be equal to CO3 2 minus, and H plus dissociation. And what is the pKa for this case? That is equal to 10.3, and that is what you see here, right. So, 10.3 and 6.3. So, as you now see, everything is in HCO3 minus at 8.3 pH, and there is no more H2CO3. So, as I keep increasing the pH, now HCO3 minus is further dissociating into CO3 2 minus and H plus here, and that is what you see here. As HCO3 minus is decreasing, you now start having the deprotonated form here, and that is what you see here, right, which is CO3 2 minus being formed, right. So, now again this repeats itself, this as in this particular part of the graph, because diprotic again repeats itself here, right. So, this is what we see here. Anyway, let us move on. Now we are going to have a triprotic acid. So, an example I guess is phosphoric acid, and I believe we are going to look at that in great detail in the next slide. So, here, and what are our dissociation reactions? H3A can go to H plus and H2A minus and so on, and you will have pKa1, you will have pKa2 and pKa3. Anyway, let me write them down so that people who have some trouble understanding thus far, it is clearer for them, I guess, right. And I think I messed something up, right. It is going to be 3 minus here, right. Okay. So, H3A is going to dissociate into H plus and H2A minus, and again this H2A minus is going to further dissociate into H plus and HA2 minus, and HA2 minus is again going to further dissociate into H plus and A3 minus. So again, so because we have, what do we say, 3 protons, we are going to have 4 ionization fractions, alpha naught, alpha 1, alpha 2 and alpha 3, and obviously each one would be equal to what now? The concentration, this will be H3A by A total, and what is A total here in this case, please? It is going to be equal to the total acid in all its forms plus H2A minus plus HA2 minus plus A3 minus, right? That is what we have here, and the second ionization fraction is going to be ratio of H2A minus concentration by A total, and the other one is going to be HA2 minus concentration by A total, and the other one is going to be HA3 minus concentration, pardon me, not A3 minus, HA3 minus, A3 minus by A total. And now again let us try to first approximate these equations. So now I am going to have H plus cube plus H plus square into Ka1 plus H plus into Ka1 Ka2 plus Ka1 Ka2 and Ka3, right, and this is what we have, and the numerator is going to be H plus cube, and same case here, alpha 1 is going to be H plus square into Ka1 by the same denominator as above, and alpha 2 is going to be equal to H plus into Ka1 Ka2 by the same denominator, and what is alpha 3 going to be equal to? It is going to be equal to Ka1 Ka2 Ka3 by the same denominator as above. So again, what will these fractions give you an idea about? Let us look at that, I guess. So I think the example we are going to look at is phosphoric acid H3PO4, I guess, right, and it has 4 species that can exist at equilibrium, H3PO4 the most protonated, all the way to PO4 3 minus the most deprotonated form, right. And so in general it has 3 pKa values, one is around 2.3, you can correct me later, and the other is I think around 6.3 or 6.6 I guess, or 7.2, I am not sure, let me go with 6.6 for now, it is an approximate value, and this is going to be 12.1 I guess, right. So 3 pKa values. So again let us understand this figure and we will be done for this session. So initially at pH 0 everything is going to stay as H3PO4, right. So at pH 1, let us say, where will be pH 1 now? So at pH 1, let us say, if I add H3PO4 to the water, so I have a beaker and the solution is initial at pH 1 and I add H3PO4, right, there will be little to no change in pH. Why is that? Most of it is going to stay in the protonated form as H3PO4 and little to none of it will dissociate into H2PO4 minus and H plus, right. So no H plus is being released or little H plus. So as I keep increasing the pH around 2.3 I guess, which is the pKa, you see that alpha 1 or alpha naught equal to alpha 1, right, and that is what you see here, and that is going to be equal to 0.5 there, and obviously alpha 2 is equal to alpha 3 equal to 0 at this stage at pKa 1 at pKa 1, right. So if I keep moving further though, and let me erase this, and now let us say if I keep moving further down in this particular range, and what do I see? I now see that H3PO4 will dissociate into H2PO4 minus and H plus, and as now you see that let us say at around pH 3, right, what do I see? Any acid that is added to the solution will dissociate into H2PO4 minus, most of it around, what do we say, 90% let us say, or 0.9 or 0.85, and very little of it will be present as the protonated form, which is H3PO4, right. And again, if I move further down the line to the pKa2 value, what is the 7 or 6.6, something like that. And what is the case there? At pH is equal to pKa2, what would I see? I guess I see that alpha naught or H3PO4, there is no H3PO4 present at 6.6, right. The H3PO4 is done here about 4.3 or so. So, alpha naught is going to be 0 and alpha 1 is equal to alpha 2 is equal to 0.5, right, and alpha 3 is equal to 0. In the same case, as we move further to the pKa3, at pKa3, what do we see? It is only going to be present as HPO4 2 minus and PO4 3 minus. So, alpha naught equal to alpha 1 equal to 0 and alpha 2 and alpha 3 are the concentrations of HPO4 2 minus and PO4 3 minus are going to be the same. That is given by alpha 2 is equal to alpha 3 is equal to 0.5, and that is what you would see here in this graph, right. So, this is at the 0.5 line, let us say, right. And so, the ionization fractions here will give you an idea about the fraction of that particular species which we are talking about in the context again. So, in today's class we have discussed mostly about the ionization fractions, right, and I guess at this stage you should be able to once you look at the pH and the alpha naught values, be able to figure out which acid you want to use. Let us say if you want to bring down the pH or the fraction of that particular protonated or deprotonated form at that particular pH for a particular acid, right. So, I guess with that I will end today's session, and thank you.